Good afternoon, all. I'm Aditya Shriwal, and today I'm going to present my topic on chaotic cryptography. It is a fusion of chaos theory and cryptographic techniques. Today, we will explore what is chaos theory, and how it is related to cryptography. So, let's begin. Cryptography is a chaotic communication via encryption and decryption using keys, which means that when we send the data, it encrypts it, and when we receive the data, it decrypts it. Now, the key which is used is of different types, like asymmetric or symmetric. In the symmetric, we use the same key for encryption and decryption. For example, we can see AES. And in the asymmetric, we use different keys for encryption and decryption. Example is RSA theory deals with a system that appears random but are deterministic. Combining them leverages the chaotic system's unpredictability for the stronger encryption. What is chaos? In general, everyone thinks it is a confusion, madness, disorder, noise, havoc, or a mess. But no, it's not like that. In mathematics, chaos is studied in the field of chaos theory. It exhibits some properties such as it should be deterministic, it should be nonlinear, and it should be sensitive dependence. Chaos theory is a branch of mathematics focusing on the complex systems like highly sensitive to initial conditions because small changes can lead to vastly different outcomes. Like we name it as butterfly effect. It is common in weather, fluid dynamics, and even population growth. The key properties it exhibits is nonlinearity, deterministic, but yet unpredictable behavior. The chaotic systems are ideal for cryptography due to pseudo-randomness, ergodicity, determinism, and these systems can be used for key generation, transformation, or encryption function. Coming to the first property of the chaotic system, that is deterministic. It means that we can formulate a equation using a mathematical model. It can be either in a discrete form or in a differential form. Here, we named it as logistic map and Lorentz system. The nonlinear is the second property, where we can see the next x is given as a feedback to the previous f of x. Here we can see if we do such system, we will get x values such as there will be no pattern found in the next x. Sensitive dependence. It is the third property of chaotic system. We can see by this metamorphic effect that at the one end of the world where the butterflies are flapping their wings, at the other end it creates a tornado, which means that if we change little bit in the initial conditions, we will get a drastic change at the final stage. Concept which we have seen in the last slide is known as butterfly effect. It is sensitive, which means the tiny changes can yield enormous differences. It is exhibiting determinism, which means that chaos isn't random. Many people think that chaos is random, but it's not random. It's unpredictable. It changes drastically that it can't be predicted. So this is very useful in cryptography. And also how we can measure this randomness. We can use this Lyapunov exponent, which measures the rate of divergence of the nearby trajectories. There are different chaotic encryption algorithms such as chain system, Friedrich's algorithm, and 2D logistic mapping. The algorithms like Friedrich and chain system based encryption enhances security, but when as it expressed as an equation, its usability is easier in an application. We can see the bifurcation diagram of 1D logistic map using this figure, as while we are varying the R value in this equation, we are getting patterns which becomes unpredictable, but it is deterministic because we can find the values of x by using this xn plus 1 equation. Therefore, it is deterministic. Now, while comparing the values of logistic map, we can see that when r equals to 2, all the values are identical. So, after increasing r to 3.3, the predictability decreases somewhat as the alternating values are only identical. So, more increasing the r value at 3.83, we can see the predictability decreases more as this value is similar to this and this value is similar to this. So, we have decreased the predictability, and we have seen that when r equals to 3.93, it becomes completely unpredictable. So this is the example in the cryptography. So if this is a key, when we are taking r equals to 2, we are getting the alternate values of key as same. But when we increase the R value, at this point we can see all the values, all the digits in the key are different and it's unpredictable. Now, there are different types of chaotic maps. Example, in 1D and 2D. The logistic maps which we have seen was 1D, and another chaotic maps are tent maps, sign maps, and Arnold cat map. Even there are 2D maps which are anon maps, 2D logistic, Lorentz affected, and this each map introduces high sensitivity and unpredictability. Now, here we can see this is a 2D logistic map. Here the equations are in the x dimension and y dimension as well. Here, the 2D logistic sequence generator is given an encryption key K, and the plain text is then goes in permutation, diffusion, and logistic transposition, and we can generate a ciphertext image that is C. This is the difference between the using the logistic map and quantum logistic map. Here we can see we are getting the unpredictability after 3.5, but we can see that the unpredictability increases in quantum world. Lyapunov exponent. It is a measure of sensitive dependence on initial condition. From this diagram, we can understand that initially the separation was well known, and after x distance, we can measure the rate of separation or the convergence of infinitesimally closed trajectories by using this expression as del t equals to del naught e power lambda t. This explains us that the separation rate is exponential. So after this outcome, we can conclude these points, and even when we see the Lyapunov exponent and bifurcation diagram comparison, we can see after 3.5 we can get the exponent positive value, and positive value means it's a chaotic. Hence, this proves that 1D logistic map shows us chaotic system. Now we will see the applications of chaos in cryptography. We uses it in image encryption, the key generation, stream cipher, and IoT security. Mainly, we are seeing in image encryption as the chaotic sequences used to shuffle and substitute the pixel values. The advantages are it is highly sensitive to keys, which means the minor change yields different output. There is a huge key space, deters the brute force attacks. Simple to implement and fast, it is a better resistant to statistical and differential attack. The challenges which are faced here is in synchronization, as sender and receiver must share the exact initial values, because if it changes the initial values, there will be a drastic change in the final output. The digital degradation is also another challenge for the finite precision, the hardware implementation, and the lack of standardization. The real-world implementations are in hybrid algorithms where the chaos plus AES improves the complexity. Even in research, a novel image encryption schemes using the 2D chaotic maps IEEE. It is used in secure wireless communication and embedded systems. This is the implementation part which I have done is like taking the original image, applying the 1D logistic map, and after that we are getting this encrypted image using the chaos. And after decrypting it, we are getting the same image as the original image. I have attached the Google Colab link here for verification. Our future scope is the quantum chaos. The merge of quantum computing with chaos can increase the unpredictability, the enhancement in the IoT security, and integration with the AI ML. So chaotic systems as the pseudo-random number generators gives us advantages in the things like sensitivity, ergodicity, and mixing properties, as it serves strong pseudo-random number generators. The advantages are the speed, complexity, key sensitivity, whereas the disadvantages are security vulnerabilities, implementation challenges, and resource constraints. A real-world use case are some secure communication and image encryption, whereas the future trends will be the watermarking and the quantum resistance. So today we have seen the potential of the chaotic cryptography as it has a significant potential, and in the future the chaos is the key to future cybersecurity. Thank you.